Hi everyone, welcome to day 17, the first of our case studies in this case study week, where we'll be putting all we've learned about cockproof to the test and thinking about a bunch of the programs that we've written before, seeing what we can actually prove about them. So today we'll be proving that insertion sort actually is a sort. So we spent a bunch of time back in day 6, I think it was, talking about sorts and what makes a sort, and we came up with a spec and some of them looked okay, but really, at the end of the day, we'd like to know with more confidence. We'd like to do some proofs. So to get there, we need to walk through the spec first and then actually do the proof. So if you look at the plan for today, we're actually going to start just talking about the permutation part of the spec, defining an inductive proposition. That's today's. We'll talk about how to interpret that computationally. We'll talk about sortedness and how that part of the spec works and how to use the inductive proposition for sortedness. And then we'll do the proof. Right, this is actually turns out not the hardest part here. It's getting to this spec that's the hardest part. And there'll be one final video where I'll be talking about, well, this was a spec that I chose sort of calculatedly to be easy to use, but it turns out it's really easy to choose a bad spec to prove with and spend a lot more energy. And there's some optional exercises to go with that part. Okay, let's get started. Let's look at our inductive proposition for talking about permutations. Okay, so to start out, we've seen permutations back in day 6. It was part of our correctness criteria for sorting. The idea of a permutation is it's a rearrangement of the elements of one list into another. So what I have here is an inductive type that characterizes permutations. We're going to do a little bit of work in the next video proving that this corresponds to a computational notion of permutations we will define. But we're more or less going to take this for granted. We're not going to fully reflect it because it turns out to be pretty hard. I do want you to get an intuition, even if we're not going to sort of validate this part of the spec. So let's start with a little bit of an intuition. We've got some exercises here meant to sort of get you started. Let's look at the int prop here first. We'll look at each of the constructors and talk about it a little bit. I think I'm just going to talk about them as constructors here. I think it's a great exercise for you to convert these to inference rules and sort of look at them that way, because I think that's actually the clearest presentation, but I think it's also really good for you to do it yourself. Okay, so what are the rules for permutation? So for any type A, we're going to talk about permutations of lists of A's and lists of A's. So this says the first list is a permutation of the second list. Now, permutation is a symmetric property, as we'll end up proving, but fine. Okay, so to start, what is the axiom or the base case? Here's a base case axiom. Well, the empty list is a permutation of itself. Right? This is sort of where all permutation proofs are going to start. It turns out we're going to have other axioms, though. I'm going to skip ahead. Perm swap is an axiom, right? For any x and y, and just a list L, y cons x cons L is a permutation of x cons y cons L. Now notice here, there's no hypothesis that of like L and L prime. This is the same tail of the list L. We're just saying a way to have a permutation is to swap the front two elements. That might be a little confusing. Well, what do you mean just the front two elements? What if I don't want to just do the front two elements? What if I want to do something else? Well, that's fine. Perm skip has your back. Perm skip says, okay, give me an x, give me lists L and L prime. If L is a permutation of L prime, then I can stick the same thing on the front of them, and they'll still be permutations. So this lets me sort of put a perm swap somewhere further down the list if that's convenient, right? So that's perm skip. We're still not there all the way. What if I want to swap an element from the front of the list all the way to the back of the list? Right? That's not right next to each other, so perm swap won't work. The last thing we have is we're going to encode transitivity as a rule for permutation. We're just going to say, look, if L1 is a permutation of L2 and L2 is a permutation of L3, then, hey, being a permutation is a transitive property, L1 is a permutation of L3. So then what we can do is we can use transitivity to sort of say, well, look, maybe I can't with perm swap directly relate the swappings that gave me one permutation to another. But with transitivity, I can sort of hop between single swap things and find a permutation that way. So I'm going to do one quick example here, and I think you'll start to get the feel for this. It takes a couple of proofs for people to really sort of like deeply understand what's going on. The CS word for that deeply understand is grok, which comes from an old science fiction book. So grok here is to truly understand in your heart of hearts. So we're gonna build up to like abstract understanding, some concrete understandings of an example, which I'm going to show you here, some like slightly less concrete understandings in these proofs, and then eventually grokking being the top of the mountain. Okay, let's walk through this proof. So here we want to prove that the list true, true, false is a permutation of false, true, true. Cool. So we can't directly apply perm swap because, okay, it's not at the front, right? True, true is not a swap of false, true, right? If you think of it this way, false moves from the end of the list to the front of the list. So what we can say is, look, we can pick at something that's kind of in the middle, like it's like partway permuted. So true, false, true is like kind of the middle ground between these two. So great, these two are permutations of each other. And now with perm trans, when we've specified the middle hop, we have to show that the left-hand side can reach the middle, and then we'll have to show that the middle can reach the right-hand side. Okay, let's see how that works. For the left-hand side, so here rather than using bullets, I've used curly braces. I think that reads a little nicer here, but your mileage may vary. So here now we have a sort of slightly simpler case. Look, the fronts are the same, and then the backs are swapped. See, true, true, and then the backs, true, false, false, true. Those are swapped. So to get that to work, we can skip, saying, okay, look, I have some x, and then the tails of the lists will be permutations, but the x's are the same. So that works. And now we have to show the tails of the list are permutations. So perm swap says, well, look, these need to be exactly swapped lists, right? The tails of the list have to be identical. It's empty in both cases. And then the head and then the head of the tail and the head and the head of the tail just have to be swapped, which they are. So perm swap works to finish that case. Okay, now we have to show that the middle relates to the right-hand side. And here we have an easier job, right? We can swap directly. True, false, false, true, and then identical tails. That's the structure of every proof with this permutation relation. This permutation invariant, this notion, this inductive proposition for permutation. Every proof is going to basically be some number of uses of perm trans, connecting skips, swaps, and nils. Right? That's all it's going to be. And perm trans is the thing that lets you sort of like slowly, move things together via intermediate hops to be able to use the swap, which actually does the swapping, right? If you look at these rules, the only thing which actually permutes, which actually changes the list, is this perm swap rule, right? You might not understand, well, why not compress it and like let L and L prime be different here, right? Wouldn't that be easier? And it turns out, well, it would make it easier to prove that something was a permutation, but it would actually make it much harder to reason about a thing being a permutation. After sort of like a fair amount of experimentation, people have decided this is the right way to frame this spec. Okay, so you have a couple of exercises to do here. One of them, we've given you an informal proof to go with it. Just as a way to sort of give yourself some guidance. But the stuff that you've seen so far should, I think, do you just fine later on. All right, so you'll prove these lemmas just to get a feel for permutation, and then we'll start looking at reflection to see where we can get thinking about how permutations relate to a computational notion of permutation. Cheers, y'all.